All right, guys. So let's see where the world gets its energy from. Okay. So this is the world energy consumption. Okay. This is uh, this is the annual world energy consumption. Okay. And this was roughly in 2020, 600 exajoules. Okay. So to run the world, like, to run the human enterprise, you need 600, so roughly 10 to the power of 9, 10 to the power of 21 joules. I guess 600 times 10 to the 18 joules per year. Yeah. So where are we getting this energy from? Okay. Right now, so here's oil contributes about, you can see 33%, natural gas about 115, so roughly 20%. Coal contributes that much. And you can see about, if you add these three, fossil fuels contribute about 80% of our energy. Nuclear energy, that's a green energy, hydroelectricity, and renewables. Okay. Now this share is getting bigger and this share is getting smaller. Okay. We'll talk about what is the problem with this share. Okay. So this is causing climate change. Okay. So let's, so these big numbers, we don't remember big numbers, so let's put it in more memorable terms. Okay. So here's the amount of energy that you need per year. Okay. And then what we'll do is we'll convert that to per second. Okay. So, and in a year, so this is the amount of energy, 365 days, 24 hours, that many seconds. Okay. And then what we'll do is we'll divide this by 10 to the power of 9 joules per second. What is this? This is a large power plant. This is a Hoover Dam. Okay. So this is the power requirement, how much energy you use per second, the world uses per second, and then we'll divide that by Hoover Dam. And so this number tells you need about 15 to 20,000 Hoover Dams running constantly at full capacity to run the world. That's what that number is. Okay, so you need about 16,000 Hoover Dams running 24/7 to run the world. And now with AI and all that, our power consumptions will go up. But anyway, so here's the deal. 80% of our energy is coming from fossil fuel sources. Okay, 20% from renewable energies. That's where we get our energy. Why do we need energy? We need energy to do work. Okay, well, what is the problem with the use of fossil fuels? Okay, fossil fuels are hydrocarbons. Okay, why are they called fossil fuels? I'm sorry? They're fossilized hydrocarbons. Hey, fellas, you're disturbing me. All right. So they're fossilized hydrocarbons, and the way you get energy is, so here's an example. Here's the way you release energy is you burn it. Burning it just means you're combining it with oxygen. Okay? And here are the products. Okay? So when you burn a fossil fuel, see, the carbon combines with oxygen and gives you carbon dioxide, and this is the culprit. Okay? And there's water vapor plus energy. Okay? Energy is in the form of heat, and unfortunately, we had to convert that heat to other useful forms of energy, electricity being the most useful form. And that heat can be converted to electricity. Only a third of that can be converted to electricity. All right. So when you burn fossil fuel, you're releasing carbon dioxide. and that leads to global warming. Okay? So global warming is one of the biggest problems facing mankind. And the only way to fix that is to flip this. You need to switch to renewables. Yeah. That will happen because right now, if you had $500 billion in your pocket and you want to build a power plant, the cheapest thing to do is that. Okay. So, but we need to do this as soon as possible. Okay. So, when you burn something, you release heat. Unfortunately, only a third of the heat is converted to electricity or mechanical energy. So, for instance, in your car, you're burning gasoline, and only about 20% of that heat is converted to the motion of the car. So, your car is about 20% efficient. Right? So, think of this: for $5 of gasoline that you put in your car, you're getting $1 of motion. Okay. And then you see a squirrel and you apply brakes instead of running the squirrel over, you know. And that dollar also goes out the window. All right. So we'll talk about the greenhouse effect. Okay, so here's the Earth, here's our atmosphere. Okay. We get our energy from the sun. The sun's temperature is about 6,000 degree Kelvin, surface temperature. Okay, 5,800 degree Kelvin, and at that temperature, what it emits is mostly visible light. So here's the wavelength of light. This is the intensity, and that's what the sun is emitting. Okay. Our atmosphere is mostly transparent to that radiation. That radiation comes through. We absorb this radiation, and then, and then we re-radiate it as infrared radiation because our the temperature of the Earth is colder, and so the radiation we are emitting is infrared radiation. So this is what we are emitting. Now here's the basic thing. Okay, if more energy is coming per second than you're radiating, what will happen to the Earth? It'll warm up. If you're radiating more energy than is coming in, what will happen? You'll become colder. All right, so, for the longest time, there was an equilibrium. The amount of radiation we were emitting was equal to the amount of energy coming in. Up to 1800s, it was in equilibrium. In the last 50 years, we are radiating less than that's coming in. Okay, so we are radiating less, and so the Earth is warming up. Okay, well, how much is it warming up? So, again, we don't want to quibble on the numbers, but in the 1800s, the average temperature of the Earth was 14 degrees Celsius. Today, it's about 15.3 degrees Celsius. Again, you can look it up and all that stuff. Okay, so you're radiating less in the last 50 years, and so we're warming up. Okay, let's look at how much less you're radiating. Okay. I'm just telling you these numbers because you will be the decision makers in the future. All right. So you're radiating about 3.2 watts per meter square less. This is called radiative forcing. Okay. Here's a meter square of ground. For every meter square on Earth, you're radiating 3.2 watts less. Okay. That's the energy consumption. Well, all right, well, let's put that number in perspective. So what does this number mean? Okay, so if you add up So that's how much less you're radiating per meter square. So if you add it up all over the Earth, this is how much it amounts to. Energy is being trapped on Earth at a rate of 1600 times 10 to the 12 watts. Okay, let's put that number. Do you guys remember how many Hoover dams do you need to run the Earth? All right. Okay. So this is 1600 into 10 to the 12. 10 to the 12 is 10 to the 9 times 10 to the 3. So this is equal to 100 times 16,000 times 10 to the 9. That's how much you need to run the world. You're trapping energy at 100 times that. Then you're consuming. You're trapping, so again, here's another way to put this. This is equivalent to exploding 20 atom bombs every second and trapping that heat. All right, so how are we trapping that heat? So what we are saying is we are radiating less heat than is coming in. How much heat are we trapping? We're exploding 20 atom bombs, the kind that was dropped a few years ago, every second. Okay. Well, what is happening when we are burning fossil fuels? We are increasing the CO2 level in the atmosphere and changing the property of this atmosphere. And it's becoming less transparent to this infrared radiation. Its property is not affecting this radiation. This radiation is being absorbed by this higher levels of greenhouse gases in the atmosphere. So we are changing the property of our atmosphere to this radiation. Okay. Well, what happens if CO2 levels increase? The infrared CO2 absorbs the infrared radiation and it re-radiates equal in all directions. Okay, so when infrared radiation is trying to go out, it bounces back and forth and gets trapped. All right, back in 1800, CO2 levels were 280 parts per million. What does that number mean? For every million atmospheric atoms, 280 of those atoms were carbon dioxide atoms. Okay. Today, it's about 420, or there's meters on the internet, so CO2 meters, it's about 430 parts per million. So you've increased it by 50%. Okay. So here's a graph. So you see this is 280 parts per million, and in the last 50 years, the CO2 levels have gone up. Okay, this was 2020, 420 parts per million. So the CO2 levels have risen by 35% in the past 60 years. Okay, well, what happens if CO2 levels rise? The temperature rises. So remember, we've gone from 14 degrees Celsius to 15.3 degrees Celsius now. You know, our goal used to be below 15.5, but that's probably not going to happen. If the temperature rises to 16 degrees Celsius, that's if the rise in temperature is 2 degrees Celsius, okay, the Greenland ice sheet will melt, and people believe that's irreversible, and you can't tell on the time scale over which it will melt, maybe 3 to 5 to 10,000 years. And if all of Greenland ice sheet melts, the sea levels will rise by 6 meters, about this much. It will displace about 10% of the world's population. And of course, the associated weather phenomena will be much stronger and all that kind of stuff. All right. Of course, that's a problem created by my generation for your generation to solve. All right, is there a solution? Okay, so let's see. This is the world energy consumption, 16 terawatts, that's 16,000 Hoover dams. See, that's how much energy you need to run the world. Look at this, how much solar energy is reaching Earth. 23,000 terawatts. All you need is not even 1 part in 1,000 of that to run the world. So you could run the world entirely on solar energy. Okay, and this graph shows you this thing. If you cover those black dots with solar panels, you could run the world. Yep.
Could there be issues with the current efficiency rate of solar panels?
All right, so you run a business, and if you have 2 lazy people, what do? You just hire 4 people.
But a solar panel requires petroleum to build.
How much is your car worth? $20,000? How much? So roughly, to build your car, whether it's an electric car or a gas car, it takes about the same amount of resources. The carbon footprint is the same. But to run your gas car, it takes about $2,000 a year. So the operational carbon footprint goes to 0. The production carbon footprint is negligible. That will not be an issue at all. Okay, so you cover those with solar panels and you can run the world. Okay, so you can see that enough solar energy reaches, you can run the world just with wind energy. You can build a gigawatt worth of plant for $3 billion. Try building a Hoover Dam with $3 billion. You could put a Hoover Dam's worth of wind power in 6 months. Try building a Hoover Dam in 6 months. It'll take you 20 years to build Hoover Dam. It'll cost you 20 times as much. Solar and wind are cheap as hell. Yeah. All right, guys. There are other stuff I can tell you about, but we'll stop here.